SwayamPrabha. Digital India. Educated India.
Hello and welcome. This is going to be a class on optical methods for solid and fluid mechanics. This course will be taught by two professors, myself and Professor Kaushik Vishwanathan. I am Alok Kumar. I am an associate professor in the Department of Mechanical Engineering. My colleague Kaushik, he is in the same department. So let's see what this course is going to be all about. Okay. So now, if I had to introduce the course, I would simplistically state that this course will deal with the use of optical methods for quantification of fluid and solid mechanical phenomena. On the fluid mechanics front, the course will focus primarily on fluid flow, visualization and quantification. Techniques that we will discuss will include shadowgraphy, particle tracking velocimetry, particle image velocimetry. The second section of this course, which is going to be taught by my colleague, that is going to focus on the solid mechanics portion, and it will cover a range of experimental methods, including strain field visualization like DIC, which is short form for digital image correlation, and other techniques such as photoelasticity. So what you can see here is this course is going to be, so I am going to be teaching till here, which is the first portion of the course. So from here onwards to here, and as you can see from some of the names, if you are familiar with particle image velocimetry, particle tracking velocimetry, these are names of all experimental techniques. Right. So you can get a feel of the course that this course is going to primarily focus on explaining the experimental techniques used for quantification of fluid flow, and then but before even that, we are also going to learn some of the preliminary requirements that are needed to understand and perform some of these experiments. The reference materials that are required for this course I have also pointed out here. So one book, for example, particle image velocimetry, it is a very nice book which gives you a nice practical guide. It's also titled a practical guide, but this goes through a lot of details about experimental handling as well as all the mathematical preliminaries that are required to understand particle image velocimetry technique. And this book is written by Raphael, Wilter, Verily and Kompan-Hans. It's a Springer publication. Now these are the last names of the authors, Raphael, Wilter, and this is one of the books that we are going to refer. And these other two books, these are going to be for the second portion of the class. So which is, again, as I said, will be covered by my colleague Kaushik. So these are the particle image velocimetry happens to be one of the most widely used experimental techniques in this area, and hence the book that I have proposed or as a reference material deals with just that. We are going to use a number of different books as we go along, and I'll try to give you as many references as I can along the way. Okay, so this is just the beginning, and for every small section there might be some other book that I might ask you to, if you are interested in looking it up in that detail, you can look up. Okay, so this is the introduction of this course, and as you can see that I focused on the two words in the beginning, the quantification of fluid and solid mechanics phenomena, right here, right. So these are our operative words, fluid and solid mechanics, right. So if I had to write, I'd just say, let's say I'm just going to quickly write this: fluid mechanics and solid mechanics. So what is common to the both of these? Obviously is the word mechanics. and it doesn't come here by any mistake. It's very important that both of these are offshoots of the overall topic of mechanics, which is a very important part of mechanical engineering curricula or any physical sciences curricula. So since we have already stated that the basis of both of these is in mechanics, let's start with the fundamental laws of mechanics that we are familiar with, and which happens to be the Newton's laws of motion, right? So now with regards to Newton's laws, Newton wrote down a lot his understanding and his propositions in the very famous book called the Principia. It's difficult to read the Principia because it's not in the kind of language we are used to now. So here I am proposing a book. If you have time, you can take a look at it. This book is actually written by Subramanian Chandrasekhar, the famous Nobel laureate, and he simplifies down Newton's Principia for the common reader, right? It's a very nicely written book, and it explains much of the details of Newton's work very nicely and elegantly, and has a lot of Subramanian's own notes on those topics. So so basically what we want to look at is this very famous equation, right, which in the case of constant mass, here assume mass is constant. Okay. So this is the fundamental topic of one of the fundamental equations that we use in mechanics. So let's try to take a look back at what Newton had said originally for this. Okay. So this is a portion from the book. This is page 22, and here I'm going to read out from what Subramanian has written here. So this is he's talking about the basic concepts, the laws of motion, and I'll just read out some of this. And so he says, I'm going to quote here: after the introductory lesson of fundamental notions, Newton proceeds to his second lesson to formulate the basis of his entire dynamics in the form of 3 laws of motion and 5 corollaries, in brackets he says, which are essential parts of the laws. Again, the laws and their corollaries must be considered in their totality and not singly. This need, was for example fully recognized by Maxwell, who reformulated Newton's first 2 laws of motion to render more precise their enunciation. In fact, Maxwell wrote a very famous book called Matter and Motion, if I'm not mistaken, and that clarifies a lot of things about mechanics. Now, let's get to the important thing here, which is the first law, which we want to read one more time. I'm sure you are all very familiar with this law. It's quite famous and something people read while they are in school, but still there's something important that we need to consider. So here, for example, it says every body continues in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. And then these are Subramanian's notes underneath it. So he says projectiles continue in their motion so far as they are not retarded by the resistance of the air or impelled downwards by the force of gravity. A top whose parts by their cohesion are continually drawn aside from rectilinear motions does not cease its rotation otherwise than as it is retarded by the air. The greater bodies of the planets and comets meeting with less resistance in freer space, so it goes to the next page, which I have here, preserves their motions both progressive and circular for much longer time. Now, there is an important thing here, which is this term called body that Newton uses. And here Subramanian makes a very nice point, and he says that the statement of the law is not precise. And he's quoting Maxwell here, since what are we to understand by body is not made clear. The statement as it stands is valid if a point particle or a rigid body is intended, but the content of the, we'll just stop here. Okay. So the point is that this word called body here in the first law, this body means a point mass Okay, so it either refers to a point mass or a rigid body. Okay, so if you are taking a finite body, then it is a rigid body, and the rigid body is a body which has infinite resistance to deformation and basically does not deform, right? So a rigid body does not deform. So that's the critical portion idea here. So Newton's laws, when we look back at it, basically is intended for either a point mass or a rigid body. Now this is where we come in. We are actually interested in understanding real bodies, bodies that are not rigid. So these real bodies, they deform, and we are interested in understanding deformation, right? So both in solid and fluid mechanics we encounter deformation of bodies, and that's what we are interested in, and not just interested in seeing the deformation, we are interested in quantifying it and understanding. So I'm just going to make this point here again. We want to understand / quantify deformation. Actually, in this particular course, we will not go so much in the details of understanding, but rather we will confine ourselves to the quantification of deformation, because that's what we are more interested in. This course is designed to be an experimental course or a prime introductory experimental course in understanding deformation. So we are interested in real bodies which deform. So Newton's laws are still applicable here, but for that we have to, it's going to now start being valid for point masses. And then if you want to understand the behavior of a real body, then you have to start from these point masses and build up from there in order to understand deformation. So here what I'm going to show you is a fluid mechanical deformation. So what we have is this, this is a fluid here that we'll see, and the experiment that we are showing you here, it's actually carried out in a cubical box like this, where there is a laser that is being shown. It's a green laser, and the laser is illuminating, this is a laser sheet which is illuminating the box, and there are tracer particles in the fluid. So okay, these are tracer particles, tracers, I'll just leave it at that. So small tracer particles are in the fluid, and what is going to happen is there is this top here which is going to rotate. So this is, as this rotates, there is flow that is going to happen in the system. So I hope you were able to see that. I will play this video one more time for you, and I want you now to do something for me, which is, when you look at this video, what I would like you to do is try to look at the particles which are moving. These are all tracers, these small green dots. These are looking green because there is a green laser that is coming from the side, and these are these small things, these are your tracer particles, right? Now the fluid is moving, so the entire body is deforming in this particular case, and from the motion of these tracer particles you should be able to visualize some of the flow that is happening. So I want you to take a look at this video one more time and try to see if you can understand how the flow field looks like. So now if you were careful enough, you could have seen that the flow is moving up here. There is this motion that is there. I think this is the correct direction. We can recheck if that is the correct direction or not. But if you see these portions, I mean, you can see flow all around, but along the wall here there is flow which is moving up. On this section you have this eddy type of situation right here. Let's just see if the arrows are correct, and of course you can now see flow at all the different points, right? Okay, my arrows were in the wrong direction. This is the flow is actually in this direction. Good. So this is this gives you an idea of a deformation of a fluid system, and you can already see why this course has been named as such. You are using light. In this case, there's a laser that is coming, and we are trying to understand flow behavior. We are visualizing flow, as well as we'll see how this kind of an image or video actually helps us quantify the flow field also. Okay, so this is specifically meant for this course, this particular video. We will use we will later use PIV to find the flow field, quantify the flow field actually. Okay. So this is one type of deformation. Let me show you a slightly different type of deformation now. Okay, this is, yeah. So so now here, what I'm going to show you in this particular video, as you can see, this is also a video that is taken using this. It involves fluids, obviously. So there is a fluid 1 here, and there is another fluid here. This is fluid 2. Fluid 1 is lighter than the fluid 1. Fluid 1 is lighter than fluid 2, so it's up, and this is the interface, right? So this is your interface. And this video is taken using a principle called shadowgraphy. Shadowgraphy was used, and I will play this video for you, and I'll just quickly tell you what's happening. There is this rod here. So this black object is the rod, and it is moving at it is going to rotate, and the angular velocity is given here. And I will play this video for you, and let's see what happens. Okay, so the video has now ended. So I'm going to play it again for you, and I want you to try and observe a couple of things. One is, in the last video, you were able to see the flow field inside, right? This time we do not have any tracer particles. So the question is, are you able to understand? There is obviously some sort of a flow field here on the side, but can you visualize the flow field? And then you can see the deformation of this meniscus, all right? So this is the deformation of the meniscus, and what happens is the meniscus rises upwards, and then later on it breaks. This breakage actually later on even causes the appearance of these small these droplets here, and it sort of becomes an emulsion on the upper liquid. So this video, while it does involve fluid flow and deformation, is a very different video from the previous one, right? So I'll play this one more time for you. Okay, so the video has ended again. So you see the video, the fluid 1 in the beginning was very clear, right? There is nothing, there's no dust particles or tracers or anything in there. It's very difficult to see how the fluid is actually moving, although you probably have a feel that there is a fluid moving. Later on, as these droplets form, the upper fluid becomes a bit unclean, or in some sense has other phases in it, and their motion gives you an idea of how the fluid is actually moving, right. So this is another type of experimental technique, and we'll talk about this also when we talk about experimental methods. By the way, if you want to read more about this paper or this type of motion, you can refer to our paper, which was published in 2022, and it discusses the physics behind this phenomenon. It's called the rod climbing effect, and this is for a Newtonian, 2 Newtonian fluids. Okay. So this gives you some idea of deformation in fluids. We now move on to deformation in solids, right. So we have solids, and solids also undergo deformation. Now what will happen is, as we'll see, the deformation in fluids is rather large, and I use that word very qualitatively here, and please excuse me for that, but I know what I will quantify that later, but right now just excuse me for that light use of that word. But the flow fields or the flow in usually fluids is extremely large, whereas solids undergo deformation. Many a times, most regular solids, the deformation is small. Okay, again, as I said, I'm deliberately using a slightly qualitative word called small here, saying that the deformations are small. I'll explain that also later, but first we want to understand deformation in solids, and this is an example of a photoelastic measurement. Okay. And what you have here, there is this rectangular bar that you see, and there is a hole here in the middle of this bar, and this is held here by clamps, and these clamps are pulling it. So this entire thing is in tension, and there are special glasses here. You can probably see my reflection. So this is me taking the photograph, and you can see my reflection in this glass. These are special types of glass which is allowing you to visualize in some sense these fringe patterns that you see right here. These are your stress fields. These are not these are not quantitative, but it doesn't tell you what is the value of the stress where there is red, and what is the value of the stress where it is yellow, but it is giving you some sort of a qualitative idea that here there are stresses are different than the places, let's say the red places are of different stress than the regions of yellow color, right. So this is another reflection, by the way, in the mirror. This is somebody else helping me out in the lab. This is from a picture when I took it when I was in Canada. So this is photoelastic measurement, and these are all small deformation problems that we'll look at. So this gives you an example of that. Here, obviously, the deformation is so small that you will not be able to see it with your naked eye, and this is obviously probably gives you an idea of what I meant by saying small and large, right. In fluids, the deformation is large enough that you can visually see it. Here the deformation is going to be small enough for you to see, small enough for you to not be able to see. Okay. This is a video that I'm going to play. This exemplifies an experimental technique called DIC, which is digital image correlation. I'll quickly explain what you're going to see here. We have again a bar that you in the background. Okay, this bar is being pulled again in the two directions, and it is undergoing a tensile test, and it's actually going to break from somewhere here. It's going to fail. Okay, breakage / failure will occur. Okay, somewhere here in the middle. What you are seeing here, there is a green patch overlaid on our actual experimental image, and this green patch is actually showing a strain value, and this is one of the principal strains. You can see green here is zero, it stands for 0. This color bar is given on the side, so you can sort of see the value. Right now everything is static, so the entire field is green, there is no strain value associated with this system. By the way, I would like to thank Praveen Kumar's lab at Material Science Department at IIT Bangalore for this particular video. So let's just go ahead and play it and see what happens. Okay, so you can see there is some kind of a fracture pattern happening here. This is a breakage that is happening. This time the strains were large enough for you to be able to see, unlike the photoelasticity example that I showed you before. You can see the things moving, but they are not moving very far away from each other than the original locations. And these are different places are undergoing different strains. You can see the change in the values of these bar graphs. So the color values have now changed, and now the red is 27 value here. So I'll play this video again, and you'll see that this bar graph on the color graph on this my right hand side, that also changes in numbers. So the numbers associated with the different colors, they start changing. So I hope that gives you a rather good overview of what deformation looks like, right? That was the whole point of it, and I tried to show you deformation, different examples of deformation. In the first case we saw, okay, in the first case we saw some fluid flow, this video, and then the next one we saw deformation of a meniscus. The fluid flow was difficult to visualize. Two different techniques are employed, and then I showed you some deformation happening in a solid body using photoelastic measurement. This is also a different experimental technique, and then here we showed failure using an exemplified technique called DIC. So these are all different videos, and this gives you an idea of what type of course material you are going to see in this particular class. This is just an introductory lecture, so I just want to give you overview of the entire thing, and in this particular module. And I hope some of you are thinking, why do materials deform? I mean, at Newton's time, he has clearly intended to take a rigid body, and after now we clearly see that real bodies do deform. So what is new? What is why do we understand why bodies deform? Well, there is a reason why bodies deform goes back to what actually forms the basis of matter, and here I'd like to involve a historical overview here. And we know that matter is now made of atoms, right? And but the idea of atoms and molecules has been hypothesized for a very long time. And for example, in India there was this famous school of thought called the Nyaya Vaisheshika school of thought, and this school of thought had thought about this particular problem as to the composition of matter, and they realized that matter is actually made out of very minuscule building blocks, so as to say. So I am going to quote from a particular book. I am going to give you the reference also, and it says the Nyaya Vaisheshika philosopher has come to the conclusion that all sensible bodies are ultimately composed of extremely minute, invisible and infrasensible particles called parmanu, atoms, right? And this book later on, so I'll also tell you which book it is. It is Studies in Nyaya Vaisheshika Metaphysics, written by S. Bhaduri. It's a pretty old book, 1947 is the publication date. And here it says, according to him, the ultimate unit of matter is not an atom but a minimal gross body, which has been called the Truti, the molecule of old philosophers. So the understanding that atoms and molecules make up matter was already there for a very long time. I mean, the Nyaya Vaisheshika school is ancient, right? It's very old, and it's interesting that they came up with this. Obviously, as science progressed and technology progressed, we gained better and better understanding of what these atoms actually look like, what are they really indivisible, or there is more to that. And obviously in the last 150 years or 200 years, we have taken massive leaps in our understanding of the atom itself. And I am just going to quickly show you this photograph. This is Rutherford, pictured, I believe, in 1905. I mean, I've taken this from Wikipedia, but the original source of this is this particular book, The Life and Letters of Lord Rutherford. And his experiments, and obviously many of his other great scientists, they proved that matter is made out of small indivisible particles called atoms, and they realized what it is made out of. There is a nucleus, there is an electron rotating around. Now, in matter, atoms and molecules can be arranged in different fashion. For example, you can have a lattice structure, and you can have atoms arranged in lattices in a crystal structure, right? So you can have a lattice structure, and you can have your atoms placed at different locations. That's what usually happens in solids. Or you can have matter, atoms bouncing against each other in no particular order, and that's what happens for your fluids, liquids and gases. So deformation of matter is basically a rearrangement of atoms at the molecular scale. To understand deformation, you actually have to understand why that molecule or atom displaced, and what is causing it, and how they were located in the very beginning, and what is their new state. We are not, in this particular course, we are not going to look at the molecular nature of matter. I mean, or rather, we are not trying to understand how the molecules themselves rearrange, but we are going to look at a more macroscopic picture of the same thing. Okay, and the macroscopic picture is going to help us out in understanding the overall deformation, and the quantification of that itself will be very, very enlightening. So this is just for our own sake, that the matter is made out of atoms, and I'm not going to go into details, but if somebody wants to later on understand the finer principles behind it, you have to look at the molecular nature. There is one more subtle point that I'd like to make before I end this particular module, and that subtle point relates, it's best to show you by example, right? So in my spare time, I like to do some astrophotography, and this is a photo from my house. This is obviously a tree here on the side, but what is interesting is these three stars are the Orion's belt stars. And in this very small box, if you have a very clear night, and if you see the Orion's belt, just a little bit below it, these are the other stars of the Orion constellation, by the way. There is a small hazy region which is, if you are able to look at it, you will be able to see that it's composed of these gases. So here, this is expanded view. These are all dots, are all the stars. This structure here, these are gases, and this is nothing but the Orion Nebula, which is a vast expanse of gases, and gases that are flowing out, and flowing out very, very fast. Okay. Fast is a relative term, and that's the point I'd like to make here before we finish off with today's class. And this is a picture I took from last year, okay, and I took one more this year, and I'm going to show you that image. It's there is a lot of noise on this side, and I'm sorry about that, but you can see the structure overall. There is a satellite trail, by the way. These lines, these are a satellite was moving across it. Now these gases, so these all red colors, these are all gases. The dots are stars. you have a strong element of flow here. You can actually see bow shocks. I mean, it's difficult with my camera, but if you have a strong enough telescope, Hubble can see it, for example. You can see bow shocks around stars. These gases are flowing out at perhaps thousands of kilometers per second. An astrophysicist can tell us better the exact velocity. But you know, I took this photo last year, I took this photo this year, and they look exactly the same. So you have this deformation, but I cannot see it, right? Why is that? You should think about it. The answer here is we have to understand whatever you want to observe, you have to have the experimental resolution to capture that. And just because there is deformation does not mean you can see it. And the resolution can be in time or it can be in space. I'm going to show you an example of resolution in time in a second here. But hopefully this tells you that just because there is deformation, that doesn't mean your experimental technique can capture it. Here for me, even though in reality the gases are moving out very, very fast, to me this is a static nebula. It's the same that was the last year, it will be the same 10 years on. The patterns will barely change, and yeah. So that's what it is. So I'll show you one more example, and I want to read out from this very interesting paper. And this paper's title is the pitch drop experiment. Okay, you can find this paper online if you look for it. And this is written by Edgeworth, Dalton, Parnell, and this paper was written published in 1984, and it describes an experiment that is actually I believe it's still going on in Australia right now. And it describes the experiment right here, that in the foyer of the Department of Physics at the University of Queensland in Brisbane, it is an experiment to illustrate for teaching purposes the fluidity and the very high viscosity of pitch, set up in 1927 by Professor Thomas Parnell, the first professor of physics there. So I'm going to not read out the whole thing, but I'll just quickly tell you what has been happening. So this is, wait, I don't think I can use my, so if you look at this image on this right hand side, you see a funnel, and the black thing inside it is star, and this star and this funnel here is cut, right? So this little drop that has formed right here, this star is actually going to flow out and actually going to form in the form of small droplets. But I think all of you have seen tar. You know that tar behaves almost like a solid body in our regular experience, doesn't it? So how come it is flowing? Well, if you have to wait really long, I mean, if you want to read the paper, it tells you the durations in which a single drop fell. So it tells you the experiment began in 1930, the stem was first cut. In 1938, that's almost 8 years, the first drop fell. 1947, the second drop fell. 1954, the third drop, and the sixth drop. So it has been falling in one drop at a time in about almost a decade, right? One drop takes almost a decade for it to fall. That also tells you that the flow or the deformation that you observe is very strongly dependent upon how you see the phenomenon, the time resolution and the spatial resolution. So these are two very important things to keep in mind when setting up experiments in order to resolve properly what you want to see. We'll not go into details of how to do that, because these are very experimental dependent or situation dependent things for you to set up. But if you ever do an experiment, you should be very mindful of both these resolutions. And for our course, we will straight up assume that you have set it up the right way. You know the time resolution and the spatial resolution required. And then we will only discuss how you interpret and how you quantify or how you process the data. Okay. So I hope this introduction gave you some flavor of what this course is going to be about, and how we are going to, what type of different phenomena we are going to look at. And I will speak to you more about the mathematical details of the course in the next coming lectures. Okay, so thank you very much.